So yeah, I have a passion for food, and perhaps what makes it nerdy is that I'm also a physicist, so I tend to put my work into what I make as food. And there's actually a lot to be understood about food, because when you prepare food, all the processes that go around, the chemistry and the physics, it's so much more better than just eating it. And to paraphrase Richard Feynman, understanding how a thing works only makes it more beautiful. So that's what I think. And that's what I would like to share with you tonight. I'm going to talk about chocolate. I picked this subject because I think everybody likes chocolate, at least I hope that everybody likes chocolate. And if there's somebody out there that doesn't like chocolate, I would like to convince you with this talk that you should. So what is chocolate? Chocolate is actually made from a plant which grows in Mesoamerica, in Mexico. And it's called Theobroma cacao. Cacao, maybe all of you have heard of cacao. The Theobroma means food of the gods. So this is quite special. Why is it called food of the gods? Well, apparently Linnaeus, who made the name up, thought it was quite special. And we know for sure that the original custodians of this plant, the ancient Maya and Aztec, thought it was food for the gods. So just to give you an idea of where this takes place, Middle America, we have Mexico on one side and the Yucatan Peninsula. This is where this plant grows. I'd like to tell you a bit about the history of cacao. It was the Olmecs in the 1500 BC that first came up with the idea to eat this plant. Because actually it gave them strength in their running and in the hunting activities. And then later, when the Olmec society died down, we have the Maya society which followed up, and they really incorporated it in their way of life. It was really a sort of a philosophy for them. Cacao also comes from the Mayan language. As you can see here, there's a glyph which depicts, it's more or less like a head, and this is how they wrote Cacao. Now the Mayans and later also Aztecs, they used to make a bitter drink, which they called, the Aztecs called it chocolate, that's our word chocolate, which means bitter water. And it's interesting to note that the timeline of the Mayans stretches quite a long way. It's interesting that it's in the middle of the Roman period in Europe, but of course in Europe we didn't know anything about South America by then. And it's quite funny to think or to fantasize about what the Romans would have done with all this cacao in their huge feasts. But the cacao only came around in Europe around 1500, when Christopher Columbus went to America and took a few of these cacao beans back to Spain to give to his king and queen as a gift. Now, in Mayan myth, cacao plays a special role. Next to maize, which is a plant which grows a lot in this neighborhood, cacao was thought to be the source of which all humans were made. At least that's what the Mayans believed. It was used also in many life and death rituals. And so in the creation myth, what happens is that a god puts his head in a cacao tree and it slowly turns into a cacao fruit. And offerings were made with frothy cacao drinks to the gods in rituals, which sometimes even involve more sinister details, like letting blood on cacao fruits, as you can see here. So the Mayans would used to cut themselves and the blood would mix with the cacao into this dark mixture, which would appease the gods apparently. Now after the Mayans, the Aztecs used cacao mainly as a currency. And According to a Spanish sailor, a rabbit, for example, cost 4 beans. The services of a prostitute would be about 10 beans. And a slave would cost 100 beans, which is quite cheap actually when you think about it, because the cacao is just found there. Now later, in the 16th century, it was actually Hernan Cortés who started plantations of this cacao and brought loads of these cacao beans back to Spain and to Europe. And this is more or less when Europe got hooked on cacao from the 16th century onwards. But it remained a drink. It was never as solid as you have it on your tables now until the late 19th century. And it's actually quite interesting that nobody thought of a way to make solid cacao. And we'll see how this happens in history. Now the way to make cacao, the cacao grows on a tree, which you can see here on the left. And actually the fruits grow on the whole trunk and on every branch. It's quite an interesting thing to see because I've never seen such a tree before in my life. And when you open them, you see this white seeds in this white pulp. The pulp is actually quite nice. Apparently it tastes like light fruits like lychee or apricot, but when you try the seeds, they're really bitter. So why would anybody start to eat the seeds? So this is quite strange. Why would the Mayans think of eating the seeds to gain some strength? I don't know. So actually, the bitterness is caused by an alkaloid called theobromine, which is quite akin to caffeine. It gives you a higher heart rate, so you can run faster and you feel more energetic. And this property was probably used by the Mayans to increase their endurance on hunting trips or different sorts of feasts. So it's interesting also to note that this theobromine is actually poisonous to dogs. Dogs cannot process the theobromine, so if your dog eats the theobromine, it stays in its body until he has heart failure, basically. So you should be careful of that. So how are these beans fermented into a nicer tasting thing? So first, during the fermentation, what happens is the pulp releases alcohol and acetic acid, which then kills the bean essentially, so it no longer sprouts. The second thing that happens is that all the enzymes within the bean start to be activated. And this actually will produce the chocolate flavor. Before that, the bean is just bitter and not very nice. But after this fermentation, you get this chocolate flavor. Now you have some beans on the plate as well. So you can try how these roasted, they're not roasted, so these are fermented beans, how they taste like. They're still pretty bitter. And I bought these in a health store, which they claim these are raw cocoa beans, but raw cocoa beans really don't taste nice, so these are not raw. In fact, the beans are slightly acidic, and this means that if you taste them, they're not very nice, they're a bit tart, and they also, if you grind them, they don't dissolve very well in water, so you cannot make really a nice drink of it. And the way you can do it, so first if you ferment the bean, you get a slightly more darker color, where you actually kill the bean. Then you roast it, and you get this nice brown bean where all the flavor really comes out. And this is what we want. So you really have to roast the bean before it tastes something like chocolate. So this is a Dutch guy who invented a process which is now known as the Dutch process. And he added alkaline substances to the acidic beans to make it a bit more palatable, to make it a bit nicer to eat, and also to make it better dissolve in water. So actually when you have the cacao, when you buy it in the shop, this is cacao made with the Dutch process. And you can use this, for example, in milk or water to make a nice cacao drink. which works far more better than just putting the cacao in water. What he also did, because he knew that there's lots of fat in the cacao, he went to the press, and with this press he pressed out the excess fat in the bean. And what you then get is a separation of the fat cacao butter and the cacao solids. You can see that here. So the white stuff is the cacao butter, which is also on the plate. And so you can smell it, and it smells really like chocolate. Of course, it doesn't taste like chocolate because it doesn't contain any sugar. So Van Houten developed this chocolate press to extract the oils from the chocolate, and he actually patented it, and in such a way that nobody else actually knew how to do it. So he had a huge head start. However, 10 years later, this patent expired, and other people got into the business of actually understanding how to make chocolate bars. And in England, one of the first real chocolate bars was made like several years later, 10 years later. And then, more or less at the end of the 19th century, in Switzerland, there was a guy called Lindt, now still known for his chocolate, who invented a process called conching. And in this conching, all the chocolate solids and the cacao butter are mixed very, very well together, and it gets a sort of a velvety structure of the chocolate you know now. And this is still used in contemporary chocolate. Everything is made by this conching process. And so what you do is you grind all the nibs, which is the solid part of the cacao, together with the cacao butter, between these big barrels, and you let this run for a long, long time. Actually, Lindt found this out when he didn't he switched off his machine, and he went away for a weekend, probably skiing or something, since it was Swiss. And then he came back, and he noticed that the texture of the cacao, which was in the machine, was really, really much better than before. Best things happen by accident. Actually, you can make cacao yourself. If you start with the cacao beans in a mortar and pestle, you just keep pounding away. First, of course, you have to peel them because the shell or the husks are not very nice to eat. So you peel them, get the inside of the bean, and you start pounding away. And you pound away. It takes a long time. After half an hour, you get something which looks like this, and it starts to get a bit sticky. You get these pieces of flakes of chocolate. After more pounding, you get something like this, but it's still a bit dry. So what we do is we warm it up. And then, if you warm it up, the cacao butter melts a bit, and you get really something which smells incredibly nice, like chocolate, and you think, wow, I must taste this because it is so nice. And then you try it, it's absolutely horrible. Why? Because it's so bitter. It's so bitter, it doesn't contain any sugar. So it's so bitter that you have to add some sugar or some sweetener to make it a bit nicer. Now, if you were to squeeze the oil like Van Houten did with his press, you get something like this. It's like a yellow, clear liquid. It's just the molten cacao butter again. And if you mix this with the cacao solids, you'll get something which is really more or less like chocolate we have today. Now, what makes chocolate so special is actually the properties of the butter. It's actually the properties of the cacao oil, the fats in the cacao. So for this, I would like you to taste. You have 2 plates. On every table there are 2 plates with a different kind of dark chocolate. And if you can taste, probably it's all gone by now, right? Yeah. So I'd like you to taste it and see whether you can detect any difference. And I'll come. Okay, very good. These are already some detectable. You ate it all, you. It's all gone, isn't it? Okay, I will teach you. I will come back to that later. So the objective here is to taste something different in the two dark types of chocolate. Okay, let me continue. So this cacao butter has very special properties from a chemical and physical standpoint, right? And I would like to explain a bit of these properties by delving a bit more into the physics of it all. So I will tell you something about the thermodynamics of chocolate. Thermodynamics is a big word, but it means nothing less than the theory of heat and temperature. And I will talk a bit about symmetries, about phase transitions, what they are and how they happen in chocolate. And I will tell you something about what is called a false vacuum. Now, the cacao butter consists mainly of triglycerides. These are just fatty acids, 3 of them stuck together on the base. That's it. And they're quite long, which means that actually the longer the fatty acids are, the higher the melting temperature is. And this is important because, you see the chocolate in your plates is solid and not liquid at room temperature. I think what we really want to see is how these triglycerides form together. Actually, you can bend them. You can bend them in a way such that you get like tuning fork structures and chair-like structures. Now, this might not be really visible from the molecular structure, which is on the left, but trust me, these are like tuning forks and like chairs. You have basically 3 types. You have the straight tuning forks, you have the slanted tuning forks, and you have the slanted chairs. They all have different properties. So what happens is that all these tuning forks or the chairs lock together and they actually form crystals, crystal structures. And these are like possible orderings of how these tuning forks and the chairs fit together. Now, as you might know, crystals have like a sort of symmetry. I will tell something more about it later. But so as you can see here, the crystals have whimsical names like alpha, beta, prime, and beta. I wish there were better names for that, but apparently they named it like this, and I cannot help, cannot do anything about that. But basically what it means is that these alpha structures are more or less like hexagonal, they're a bit loose, and they have a low melting point. The beta prime are a bit more tightly packed. They're a bit better fixed together, and they have a rectangular arrangement. And the beta ones are really tight and have the highest melting point. We could make an analogy with a car park. So the beta crystals are more like a Japanese car park, in which you have very, very high difficulty of getting your car out once you have it in there. While the alpha crystals resemble more the same car park like after a tsunami. They're scattered all over the place. It's pretty easy to find your car, although you have to find it first. And the beta prime crystals are somewhere in between. I want to say something about symmetry of these crystals. So let's take a brief detour to see what symmetry actually means. What is a symmetry? A symmetry is actually something that when you can change something and in the configuration, for example, and it still looks the same. So for example, we have on the left side we have liquid water, and we can rotate it a bit, and actually, well, it doesn't change that much, right? On the right side we have a crystal. It's ice, it's a water crystal. If we rotate it a bit, it doesn't look the same as before. Actually, we have to rotate it more, and then it looks the same. So, we say that the ice crystal has a 6-fold symmetry. You don't need to understand why 6-fold, because it has 6 sides, but that's not the point. The change from the liquid to the solid has actually changed the symmetry. This is important. And crystals usually have fixed amounts of symmetry, and liquids don't. They have symmetries all over the place. And phase transitions, so they change these symmetries. Now, in chocolate we can also have phase transitions. Let's do a little experiment. You can actually do this yourself. What do you need? You need the cacao butter for chocolate. Cacao butter is better because it's transparent. One Soviet microscope, one iPhone, one eraser to balance it, a whole lot of sellotape, and some patience. Yeah, it really is Russian. And what do we see? Well, we see something like this. There's a crystal on the left side which I took off the internet. It's magnified far more than the crystals on the right. But you can see that there's something forming, right? The blue thing is the liquid, and the yellow stuff are the crystals. And slowly something is forming out of the molten cacao butter. Okay, I just put some music on it because in fact it's not so great to look at. But actually you need a bigger microscope to see it, to really see the crystals. But in any case, it's interesting. But what is actually happening when our crystals are solidifying? These are the phase transitions from the molten phase into the crystalline phase. So the phase is actually it describes arrangement of the atoms, of matter. It's just an arrangement. For example, we have ice, which is common in water. We have fluid, like liquid water. And then we have steam, it's the gaseous phase of water. And these phases, they can transform in each other via phase transitions. And there's something interesting in these phase transitions, because when these phase transitions happen, they do so at a certain temperature. The temperature rises when we put in energy in some system. We just heat the system, we put a gas flame, and the temperature starts to rise. And actually the temperature is a measure of how fast the molecules are wiggling about. So if they're solid, relatively cool, they wiggle slowly. If they heat up, and they're liquid for example, they wiggle a bit more fast. What happens in between? In between, we have these horizontal lines where the temperature doesn't change. Why is that? We keep on adding energy, so we expect them to wiggle really a lot. But actually, that's not true, because in the wiggling, they are bound together, like little springs. These springs have to be broken. So this is what happens in the phase transition. The springs break, this costs energy, this is why the temperature stays the same. And if we go to the gas phase, we see that all the molecules wiggle about very fast. So, in the end, we're left with such a picture in which the horizontal lines are the phase transitions. Now, something similar has been measured in chocolate or in cacao butter. It looks a bit like this. We can again distinguish alpha, the beta prime crystals, and the beta crystals. Actually, I didn't really tell you the whole story here, because for water we have 3 phases, but for chocolate there are much more. Actually, there are about 6. But we don't really care about all of this complication, because the only structures which are really, really important are these 3. The alpha, the beta prime, and the beta. Now to tell you something about symmetry breaking. Each of these crystals has a different symmetry. So we saw that the ice crystal has 6 symmetries. And I don't know from the top of my head what the symmetries are for the alpha, beta prime, and beta. But each time you step one step higher, so from alpha to beta prime, you actually go lower in symmetry, and from beta prime to beta, even lower. Like from liquid water to ice crystals. And I want to tell you something about how this change in symmetry has to do with the energy. This is a bit complicated. And I completely forgive you if you don't understand this. But we can turn it all around. So what happens if the chocolate loses energy? We cool it. It's a bit like a ball rolling down a well. It loses energy. But we have these three phases. So in fact the chocolate can get stuck in one of them on its way down to the complete bottom. Well, physicists, especially particle physicists like myself, like to refer to such a local dent as a false vacuum. Because it's not the true vacuum, it's not the true ground state, it's not the lowest energy state of the system, which is beta. We can go all the way down. But if we get stuck here, we say that we get stuck in a false vacuum. Now, notice also that it's harder to get the ball out of the lowest well than it is from one of the wells on top. Right? It's harder, you have to expend more energy to get it all the way from down there to the top than just a bit up. So this is how the complete picture looks. We have two unstable or false vacua. We have one true vacuum, and there's the solid and liquid phases. Now this can happen all over the chocolate when you start solidifying it. All these crystals can happen anywhere. So you get these domains of alpha there, beta prime there. But actually what you really want, is the true vacuum, which is the most stable kind of chocolate you can have. So we have to try to get this most stable vacuum. How do we do this? So if we turn this around, just flip it over, we can see how this looks in real chocolate. There's a picture for this here. This is real chocolate. This has been measured. This is the energy that you put in to melt a certain crystal. So you see beta, beta prime, alpha. There's even a small one, gamma, but this is negligible. It's so small that we never really bother with it. And this process of getting the most stable crystal structure is called tempering. Tempering the chocolate. And must be done well for good chocolate. Some say it's an art, but it's really a science. And our knowledge of different crystal structures and the melting points enables us to actually know how to do this. So what you do, how do you choose your vacuum? How do you get the right crystal structure? Okay, let's say we melt all our chocolate. Now, we have a soup. It's liquid. If we cool it, we start to get some crystals here and there, but they're not the right crystals. In fact, when we start to cool it even more, we get even more crystals. But you see, they're not the right ones, because we only want the beta ones, the red ones. We have alpha and the other ones. So what do? We slightly raise the temperature just below the melting point of these beta crystals. We get rid of all the other ones, we are left with only these. And now we can use these as seeds to grow all the beta crystals. This is called tempering. And this is what chocolatiers do in their normal business to get the right chocolate. So you can do it by cooling, but also by cheating somehow. You can put in the right seeds already, if you have them somewhere. And you can make the seeds by shear. So what do we want? We want these slanted crystals, right? So if we press on the chocolate hard enough, we can actually form it that way. And this is called tabling. And I have a small video about this. So what do? You pour the liquid chocolate on a table. That's probably why they call it tabling. And you start to agitate it, you start to shear it, you start to press down on it, and you do this long enough. And at a certain point, you mix it up again, you agitate it. You do this for a while. It can get exhausting. At a certain point, you see that the viscosity, the stickiness of the fluid is changing. There's something happening. So you measure it, you measure the temperature, and you see, we're still above the melting point of all the other crystals, which is good. We just continue for a while more. And then a good chocolatier can notice by the viscosity or the stickiness of the chocolate when it's finished. Then he knows we have only got the beta crystals in this batch of chocolate. Then we put it back in our molten chocolate, and we let the magic happen. And the magic is the beta crystals start to grow on these seeds by themselves. And there you have it. This is the process of how you actually make good chocolate. Now, do these transformations of alpha to beta prime to beta only yield good results? No, not necessarily, because there's one energy or one crystal configuration which I didn't show you yet, and this is called the beta 6, which is the white bloom you see on old chocolate. When you leave chocolate for a long time, it will decay even further into an even lower energy state, which is characterized by this whitish tarnish on the outside of chocolate. Now, it's not really, it's harmless. I mean, you can eat it, but it's not very nice. It's not crisp. It's very soft. And the solution to fix this, like this is how it looks under an electron microscope. So the solution to fix this is just to retemper your chocolate, melt it, do the whole process again, and you have perfect chocolate again. So, this is basically what I wanted to say about chocolate. I mean, all you really need is love, but a little chocolate now and then doesn't hurt, right?
Thank you, Gabriel. I think that the chocolate will have finished by now, I fear. But I suppose there are also questions over there.
Two questions. When you have the wrong vacuum, is it cheap chocolate then?
No, it's not. It's not necessarily cheap chocolate. No, this has nothing to do with it.
Okay.
It's more about the process of getting there. So if you have like a cheap manufacturer maybe, but the chocolate type is really not important.
Okay. The second question, you have to put crystals to it, sugar. Can you also put honey in it
Yeah,
to get
sure.
good chocolate, or is then the chemical process wrong?
No, well, honey is actually 98% glucose anyway, so yeah, I mean, it's the same stuff. Yeah.
I actually have a question for Gusti. Could you evolve chocolate?
Yeah.
So the question is, could you evolve chocolate?
Yes, actually we do, and there's another person in the room who can answer this question even better. That is Elko, who is doing evolutionary art, and he is master in aesthetic selection. So we could do some aesthetic selection with our tongues. Can we? Sure.
Thanks. Over here.
Maybe you can say something about why some food works really well with chocolate and other food doesn't. Like, I know white chocolate and caviar works.
Okay, yeah, that's a totally different subject, but yeah, I can say something about that. There is a theory on how smells work, how flavor works, and this has to do with the vibration of the molecules. And apparently, when flavors fit well together, the vibrations have the same, fit in the same spectrum, basically. This is what I know about it.
Hi. First of all, thank you very much for the chocolate.
You're welcome.
Second, the tempering you mentioned. Why is it not possible to just slowly lower the temperature until these first hard crystals form and then use them as seeds by slowly lowering it further?
You can do that, but it takes a very, very long time if you let it cool slowly. And besides, when you leave it to cool, you always will get some crystals, so some other crystals. So it's slightly more inefficient, let's say.
Well, I'm going to ask the last question. How do you know all this?
Research.
So yeah, on that note, we're running a little bit late, so I'm just going to finish by thanking you very much for your very enlightening talk. I think we will have much chatter about this in the after hours. I just want to leave you with, well, I was in the comic book shop, and it's a very resourceful comic book shop, and I was sure there was something about chocolate, but there wasn't. There was no X-Men and the chocolate universe, there was no Suske and Wiske and the chocolate cherry. There was just basically nothing about food. It was all about bionics and about hell and about... So I guess next time in Nerd Night when we have a talk about metal, I will have no trouble finding a present for the speaker. But this time it was hard, so I ended up with something which was at least about food, and also because of the weather, I thought it was good to end with a positive note. So I hope that we will barbecue a lot this summer. And can you barbecue chocolate?
Sure, if you do it quickly enough, then let it melt of the barbecue.
So this is a guide by Dirk Jan, who maybe some people in the room will know, and who's going to tell us how not to barbecue apparently. So thank you very much.
Thank you very much. Bye-bye.